Hello everyone, we will continue our lectures in this optimal control guidance and estimation course, and this is a different topics somewhat related, and we need that sometime, and hence I thought I will cover one lecture at least on this topic actually. This is called discrete time optimal control. So far we have seen everything in the continuous time domain all the time. We talk about x dot equal to f of x u and the lambda dot and things like that. And many times discrete time formulation also has some beauty, and we can design algorithms in a better way and things like that way. Okay. In fact, some of our algorithms later that we discuss in this course will actually rely on this discrete time optimal control. So, this particular lecture I will just give you some sort of an overview of that, including generic theory followed by LQR in discrete time as well actually. Okay. So, that is the motivation for this particular lecture. So, outline happens to be something like this. First is generic formulation, and essentially again will lead out, it will lead us to this necessary conditions of optimal AD. Then one example will follow, and then we will move it to some discrete time LQR design. And in for your information, this MATLAB also has a DLQR function. DLQR stands for discrete time LQR actually. Then on the way we will also see an idea, one of the very earlier ideas, okay, how people thought of solving in LQR formulation using discrete LQR sort of ideas in least square setting basically. So, you convert the entire formulation, take the discrete grid points in time, and all the state vectors are equivalently converted to some sort of a control vector and all that actually, then an initial condition of course. Where the initial condition happens to be just a time, I mean just a number, it does not play a role in terms of minimization, maximization like that, and things like that. So, I will take you through that when in that appropriate slide actually. Then we will also have some sort of a discussion on discrete time LQ tracking problem. So far we have been talking about regulator, all that, the LQR, R stands for regulator, but if you really want to extend it for tracking applications, this is called something like linear quadratic tracking problems. Okay. Similar concepts are available in continuous time as well, and we have actually talked a little bit about that. I will talk more in the SDRE setting when we talk about SDRE lecture as well. But here we talk about discrete time LQR and discrete time LQ tracking issues, tracking problem. How will you formulate? How will you get a solution like that actually? So, this is what is coming up in this lecture basically. So, here is a equivalent representation of optimal control problem in discrete time. The performance index happens to be something like this, and this is the terminal penalty and this is the path penalty sort of thing. And when you talk about discrete time, there is no specific advantage of having a linear time invariant or time varying system. So, everywhere we will consider as much as possible, these are all time varying things actually. So, L can be a constant function, but L can be different at different points of time also. That is why this Lk is represented here. Okay. K stands for K varies from I initial condition I plus 1, I plus 2 like that up to n minus 1, and actually it will lead to this xn in system dynamic equation. This is the system dynamics. Okay. So, xk plus 1 is a function of xk uk. Most of the time you will see that L and F, these are all static functions, they are functions of x and u, but the function itself do not change with time. Okay. But as I told in discrete time that has no specific advantage. So, for generality, for more generic results and all that, we will consider that f can be a function of time as well. That means, the very nature of f can differ from time to time actually. Yeah. Similarly, L can be, L can have time dependence as well that way. Anyway, so this is your performance index. Okay, this is the path constraint, all happening in terms of discrete time actually, and very easily if somebody wants to really see what is how it can be done and all that. Okay, this okay, this can be done something like if you have x dot equal to f of x u, then you can do this xk plus 1 minus xk by delta t. This is the approximation of x dot, and the right hand side is xk uk. Okay. And then you can write xk plus 1 is nothing but xk plus delta t times f of xk uk. So, okay, so that is nothing but this is Euler integration actually. Okay. So, if you use Euler integration formula, then you can see that x k plus 1 is nothing but some function, okay, f k, okay, of which is nothing but x k u k, assuming delta t to be constant actually. This is how from a continuous time representation you will get a discrete time representation actually. Okay. And you can use various integration formulas to get there as well. This, okay. All right. So, this is what I was talking actually. So, we have a similarly you can discretize any continuous time cost function as well using this trapezoidal rules and all that. You can we can do that and then write it an equivalent cost function for a continuous time problem as well. So, this is our discrete cost function and this is our discrete state equation. So, with respect to these two, okay, the augmented performance index can be written something like this. J bar is nothing but this part plus summation of all that, okay, and this is what we did here is earlier is lambda t transpose times f minus x dot, if you remember that in continuous time, okay. But here in discrete time what we write here is lambda k plus 1, okay, transpose times this one minus that one, that is f k minus x k plus 1 is nothing but 0. That part is put here actually, okay. And just a comment that multiplied associated with f k here, f k minus x k plus 1, this is what is getting multiplied is lambda k plus 1, it is not lambda k, that is one of the major differences really, and that is done typically to get some nice results later basically, okay. So, that means if you see an optimal control equivalence and all that actually that way, then x k is equivalent, I mean x of t is equivalent to x of k, u of t is equivalent to u of k, but lambda of t is equivalent to lambda of k plus 1 really, it is not k. That is the difference from continuous time to discrete time really. Anyway, this is our augmented cost function, okay. And then we will follow with our necessary conditions of optimality and all that. So, for first you define in Hamiltonian h k is nothing but L plus lambda transpose f. So, L is nothing but L k plus lambda transpose this part, this part, whatever you have it here, that is what is represented there actually, okay. This Hamiltonian h k. Okay. Remember, it is a function of x k, u k and lambda k plus 1 and define something like this. Okay. Now, with respect to this definition, J bar can be written something like this, and here it is not from I to n minus 1, but we take it out from I plus 1 to n minus 1 and write the I separately basically. This is just a manipulation sort of thing, okay. So, this one, okay, I plus 1 to n minus 1, okay, whatever we have here, the very last one will also turn out to be lambda n transpose times x n, that also is that also is separately written actually, okay, here, okay. The very first one is taken out and the very last one is also taken out actually, okay. Last one is here and first one is here, in between terms are written something like this actually. Next, we want to examine the increment of J bar due to increments in all variables x k, lambda k and u k, and here the assumption again is the final time, and that is in discrete notation it is nothing but n is fixed actually, that is the definition, I mean that is the assumption here. So, we are talking about a fixed final time problem sort of thing actually. Anyway, so this is J bar which is given this one. Okay. By the way, I have taken all this material from Frank Lewis book actually. So, if somebody is interested, then they can use this Frank Lewis book. He has different versions of the book and all that, but I have used it for some of his earlier books on optimal control actually. Anyway, so this is what it is. J bar is something like this actually. Now, we are ready to apply our optimization conditions and all that. So, what you are interested in to see is the first deviation of J bar is equal to 0. Remember, there is no variation now. These are all discrete variables actually. So, we talk about first deviation of J bar has to be equal to 0, and hence we are interested to see what expression it takes first deviation of J bar. So, d J bar, if you talk about this expression, happens because of several perturbations actually, okay. Perturbation of J bar, that is d J bar, happens because there can be a perturbation of dxn, xn, that is dxn, there can be something like d lambda n, there can be something like dxi, duy, d lambda I plus 1, all sort of things actually. So, you have to see carefully this expression, what all is a function of, J bar is function of what all variables, and then keep on doing this partial derivative sort of thing, and then write this expression actually. So, to begin with, let me explain one or two expressions. If you see this expression especially, the perturbation of J bar can come through the perturbation of either x n or lambda n actually. So, this particular term. So, we write del of this term del by del x n into d x n plus del by del lambda n into d lambda n of this square bracket sort of thing. So, if you take this expression, we write it, this is what we are analyzing actually. So, first I will write this expression something like perturbation with respect to x n, and then perturbation with respect to lambda n. So, that is what we are going to do. The first term is nothing but this, first term is nothing but this, because this entire term del by del x n of the entire term is nothing but del phi by del x n minus lambda n, this one transpose times d x n plus this del by del lambda n, which is minus identity. For this does not contain any lambda n, only this one contains lambda n. So, del by del lambda n into d lambda n, that will give us this term actually, x n transpose times d lambda n. Then we will come to the next expression. Next expression is a function of x I, u I and lambda I. So, the perturbation can come from all the terms. So, you can write del h I divided by del x I transpose times d x I plus del h I by del u I transpose times d u I plus del h I by del lambda I plus 1 transpose times d lambda I. They are all simply bookkeeping actually. You observe that this is a function of x n and lambda n, hence you took the partial derivatives that way. You observe that this function can be a function of x I, u I and lambda I plus 1. So, you do these three expressions, that results in that. And then coming to the last expression, now remember h k can be a function of everything else, x k, u k and lambda k plus 1 also basically. So, you account for that. To account for that, we take all the partial derivatives like that, and then express in the form of like this actually. Remember, this is this one will give us a perturbation with respect to lambda k also. This will give something like h k is a function of lambda k plus 1. So, the perturbation will come from lambda k plus 1 because of this term, and there is a perturbation of lambda k because of this term actually. This is just nothing but a very careful bookkeeping of what all things can happen from first derivative sense actually. Once you write it carefully, then it is time to kind of put them together wherever is relevance things and all that there. So, then I keep the first term as it is, and then this one whatever you see here as it is like that actually, and wherever possible I can combine that now, and I can play around with this indice again. This is k equal to I plus 1 to n minus 1, here it is I to n minus 1. That means, wherever you see I terms, if possible I can include that within this term here also actually. If I separately write k equal to I outside, then whatever terms are there I can bring it inside by changing the augmentation from I plus 1 to I here. So, that careful notation if you can see, here it is I plus 1 and here it is I basically. That will observe two terms actually. And similarly, you can have a bookkeeping and then tell this will be like this form, this will be this form, and that will be that form. I strongly suggest that all of you actually at least do one time this algebra. It's fun to do, and it's good to do, and it will give you a lot of confidence also what you are doing actually. So, for the sake of time I will not explain term by term, but this algebra is correct actually. So, this has to be equal to 0 with respect to all possible deviations actually. That means, as before, all the coefficients have to go to 0. Now, if you notice that, then all the coefficient happens to 0. So, what about this? This will give us nothing but the state equation. Del x k plus 1 is nothing but del s k by del lambda k plus 1. And what is del s k by del lambda k plus 1? This is the only term. So, that is f k. So, what you are talking is x k plus 1 is equal to f k. That is nothing but the state equation. That is how you get it there. Similarly, for the co-state equation, you see this expression actually. Lambda k is nothing but del s k by del x k basically. So, that is what you will get co-state 1. Now, optimal control you will get from here del s k by del u k equal to 0. And then boundary condition happens to be from this expression actually, lambda n del phi by del x n, that happens to be there. Anyway, so these are the set of equations that you will have to handle it. You can carefully note that what we heard earlier is the lambda dot is minus del h by del x, and here it is lambda k equal to del h by del x. So, that means to retain this, that lambda k plus 1 taking taking lambda k plus 1 here helped us arriving there actually. If you take lambda k, then the expression will be something different. Okay. That is the beauty that that some people agree that okay, there is a systematic representation of that actually that way. That is one thing. Second thing is the lambda dot happened to be minus del h by del x. Here it is plus, it is not minus actually. Okay, all other things are similar, but this observation of this co-state equation should be noted very carefully actually. Okay, the state equation very similar to what we had, optimal control very similar to what we had, and boundary condition also very similar to what we had actually. Okay. But the co-state equation happens to be slightly different. That is what you should note it carefully actually. And again I emphasize lambda of t equivalent meaning comes through lambda of k plus 1, not lambda k. That we should never forget actually. Alright, so this is how the necessary conditions, and let us have an example to demonstrate how to use these necessary conditions and all that actually. So, we will start with we will take a linear system with a quadratic cost function. Essentially, it is an LQR problem, you can think about that, but it is a kind of a hard constraint problem. In other words, even though it is a scalar problem and all, what you are demanding that at k equal to n final time, xn should be equal to Rn actually. Okay. So, this is the system dynamics, this is the problem. We have a linear system dynamics and we are kind of coefficients. Objective is to minimize the control energy subject to this final condition. Xn has to go to Rn, there is no choice for the other things. On the way, it has to minimize the control leakage actually. So, with that formulation, we will proceed to the definition of Hamiltonian. Hk is nothing but Lk plus lambda k plus 1 transpose times Fk. Okay. With Lk, you can substitute what is that, half of r times uk square. So, half of r times uk square plus lambda k plus 1, there is no transpose because it is only single equation anyway here. So, this is lambda k plus 1 into x k plus b u k, that is from the system dynamics. Okay, that is the definition of part of it. And from optimality conditions, we have this state, co-state and optimal control equations. So, state equation is given like x k plus 1 is x k plus b u k, same state equation that we started with actually, same thing. And the second equation is lambda, co-state equation, lambda k is nothing but del s k by del x k, which is equal to a times lambda k plus 1. Okay. And del h k by del u k happens to be something like this actually. Okay. Del h k you know, right, h k is like that. So, del h k by del u k, you will see the one term will come from here, which is r times u k, plus one term will come from here, which is nothing but b times lambda k plus 1. Okay. So, essentially it is very close to what we know in continuous time, but the variables are slightly different and things like that actually. So, if you solve this equation 0 equal to r u k plus b lambda k plus 1, then u k happens to be something like minus b by r into lambda k plus 1 actually. Okay. So, very close to what we know before, this kind of problems, we have seen examples also, but the only difference is it is not lambda t, but it replaces lambda k plus 1 actually. So, as long as we know lambda k plus 1, we have got the controller actually u k. Okay. The question is how do you know lambda k plus 1 actually. Okay. And also the boundary condition sense, what you are having, you have an initial condition which is fixed, state is a fixed number sort of thing. So, dx naught is 0, and final condition is also fixed, xn has to be equal to Rn. So, there is no deviation on that, that is dxn has to be 0. So, these two happen to be the boundary condition that acts on this problem actually. So, what we do? Why to go ahead and solve it? So, what we do first is you find lambda k from 5 and 8. So, whatever these equations are there now, you try to solve it actually. Okay. So, what you are having is u k is there. Okay. So, this u k expression you substitute here. Okay. So, you write the state equation like this basically. Okay. Just for sake of simplicity, that b square by r you define gamma and then write it that way, just for the sake of simplicity sort of thing. Now, that is fine, that is the state equation, but you cannot really go ahead and solve it this equation, because the x k is left, x k plus 1 is left hand side, right hand side lambda k plus 1 and things like that. But what happens here, this particular problem, this equation happens to be independent of state actually. This is self-contained sort of thing. Lambda k is nothing but A times lambda k plus 1. So, we can solve it because it is a difference equation involving only lambda. So, you can solve this difference equation. Remember, it is a difference equation, not differential equation actually. Okay. Is this difference equation has a solution like that. It is very easy to derive also. In other words, if you know this recursive relationship sort of thing, right. So, you have lambda k is given something like this. That means, if I just start from there, okay, which is nothing but lambda, let us say n minus 1 is nothing but A times lambda n using this relationship what I am talking here. Okay. So, similarly, if I take lambda n minus 2 is nothing but A into lambda n minus 1, which is nothing but A square times lambda n minus 1. Okay. Similarly, I can write lambda n minus 3 is nothing but A q times lambda n minus 1 lambda, well, to erase that. A q times lambda n basically. Okay, sorry, there is another mistake also there. This minus 1 should not be there. Okay. All right, so this is what it is actually. Okay. You start with this expression, then you can write lambda n minus 1 is nothing but A times lambda n. And lambda n minus 2 is A times lambda n minus 1, but n minus 1 is again that I can substitute it back. Happens to be A square lambda n. Similarly, lambda n minus 3 happens to be A q lambda n and things like that. So, as in general, I can write a solution lambda k plus 1 is nothing but that kind of thing actually. Okay. But this solution is okay, but the problem here is lambda n is unknown and hence the difficulty actually. Okay. Lambda, okay, remember lambda n is not known to us actually. So, otherwise you could have gone ahead to solve it actually. But anyway, so now what you do is you have this expression now. So, we substitute it back here. Okay. This expression is available. So, lambda k plus 1 is here. We substitute it back, we get it something like this actually. Okay. Now, what happens? Now, lambda n we do not know, correct, that is not a problem, but lambda n is not a dynamic variable, it is just a number sort of thing actually. So, there is some sort of a number, even though we do not know it, it is not a changing number sort of thing, it is a fixed number. So, we can interpret this difference equation, state equation as some sort of a difference equation with a forcing function sort of thing. So, this is right. So, with the forcing function being this one, okay, this is a difference equation with a forcing function coming from this actually. So, this equation we can have a solution. If you are interested, you can derive it yourself, or you can see some sort of a difference equation math books and all that. That will tell you very clearly that if you have a forcing function like this in a difference equation, then the solution turns out to be like that actually. Okay, remember, lambda is still unknown. The solution form we know now basically. Okay. So, this turns out to be, you can write it something like this. Okay. Right, and then you have this coefficient geometric series sort of thing, right. Yeah, once you have this kind of a summation term, it is nothing but 1 plus 1 by a square plus 1 by a fourth like that actually. Okay. So, this term has a geometric formula. So, using that this series formula I can write it this way actually. So, I got some sort of a solution for the state. The only problem still here is lambda n is not known. So, x n, if you get a x k like that, I can also write x n equal to something. Okay. Okay, and this expression I can define some terms and all that, so that I can write in a simplified terms actually. Okay. So, x n is nothing but some coefficient times x naught minus some other coefficient times lambda n actually. And here is the case. Now, what we know in the problem definition, x n has to be equal to R n. Okay. So, now we have a formulation, we have a solution which talks about something into x naught which we know and something into lambda n which we do not know. However, x n has to be equal to R n, that is the constraint. So, if you have to put R n here, then you can actually solve for lambda n, that is what it is done here. If I substitute x n as R n here and then solve for lambda n from this equation, then that is what I get actually. Okay. Now, we got a solution for lambda n actually. Once you get a solution, your co-state equation is well defined now, because co-state equation happen to be this expression. Now, lambda n is available. So, you can substitute that and hence you get lambda k, and finally, the optimal control happens to be a function of lambda k, right, u k. Okay, let me see that, this one. Okay. Once you get lambda k solution, you can lambda k plus 1 is equivalent to that, then you can put it back here. So, all that is done, and you can write it as uk is nothing but something like that actually. Okay. Now, what can you observe here? There are a couple of nice observations first. The first observation is in this problem, both the final state as well as the optimal control, that means xn, which is Rn, which is a fixed number sort of thing, as well as the optimal control expression, what you see, are actually independent of the weighting function R, weighting matrix R. This is Rn is the reference signal at the end, and nothing to do with the cost function R. See, we started with a cost function R actually here. So, this R does not play any role actually. Okay. And this is also logical, because ultimately your aim is to take x to some final desired value, and on the way you are not kind of comparing with state minimization and control minimization. Your objective is only to do control minimization. So, whether you minimize some sort of a uk square or some factor of uk square does not matter actually, some fraction of uk square or whatever that is actually. So, essentially the control is independent of that, which is logically makes sense as well. Another observation is the control is actually an open loop control, because what you see here, it actually depends on x naught, nothing else actually, and Rn, which is okay. So, of course, that is where you want to go, is a function of x naught and Rn, and everything else is a system parameter a and b, but it has nothing to do with state some sort of a solution basically. So, in other words, uk we did not get as a something like minus k times xk sort of thing. Okay. So, we did not get that actually, but essentially it can be done. We will see that in a while, that discrete LQR setting it can be done actually. But this particular way of getting it, we need not get a state feedback solution, we got a open loop solution actually. Now, the optimal state trajectory, somebody can ask like that, then you can go back to this expression what you had for xk. Okay. Xk solution is available, you can substitute lambda n and you can get this xk optimal state equation also basically. Okay. Optimal state trajectory can be dictated by this is nothing but the state equation by the way. What you have is xk plus 1 is nothing but axk plus buk. Okay. And b times uk happens to be something, even uk you know, and b times uk bb will cancel here, whatever you have is nothing but that actually, that is all. So, this this is we want to do not need a solution for xk, because this is a sequential equation sort of thing, the recursive equation sort of thing. If the moment you start with x naught and you just put some formula here, k varies from 0 to n minus 1 anyway. So, if you just put varying that, you keep on getting numbers here basically. Okay. If you want a solution in xk, then that is the expression that you need to use directly. Okay. But otherwise this is good enough actually. Okay. But also remember this one, the state trajectory is again independent of both R and B, okay, and all sort of things actually. Then x naught star is nothing but x naught or xn star is R, and sometimes when you see books star notations, these are all optimal trajectory sort of thing. So, whenever you get an optimal trajectory, sometimes people put star there just to differentiate between non-optimal to optimal trajectory sort of thing actually. And optimal cost can also be given as something like this. Okay. Okay. Now, again it turns out that okay, this is nothing but this 0 input response and things like that, actually what you call each other that way, but I will not talk too much on that. The whole idea here is, because the cost function is like this, the moment this is different from this is nothing but 0 input response. Okay, this is not difficult, I can also tell about that actually, why not. So, you have this xk plus 1 is nothing but axk plus buk. So, when uk turns out to be 0, okay, all of the uk's turns out to be 0, okay, then what happens, xk plus 1 is nothing but axk. Okay. So, what will your trajectory be? If you start with the k equal to 0, then it is x1 equal to x naught, and then x2 equal to x1 ax naught, and similarly x2 equal to ax1, which is nothing but a square x naught, like that actually, right. You proceed like that, what we discussed, something very close to what we discussed before, and ultimately you will tell okay, that if I end up with xn, where it should be an minus an times x naught, using this formula sort of thing what you have here. Okay. So, that is your zero input response basically. If you do not have any control, that is where the trajectory will evolve actually, right. Now, with control something this is the cost function. That means, if this one what you see here is very different from this, then obviously your cost is going to be more, which is very natural also. Suppose pictorially speaking, suppose your zero input response takes you there, but your target is somewhere here, then you will get something like a deviation like that. If your target is somewhere here, then you require more control to come here, like that actually. So, whatever this difference plays a role, whatever difference you see here actually, okay. That is the message here, which makes a lot of sense also. Anyway, so now there is a different concept. What we got is a generic framework. Now, is there any equivalence of discrete time LQR also? And the problem is something like this. We have in general, we have something like this, xk plus 1 is ak xk plus bk uk, and performance index is very close to what you have seen in continuous time. Okay. All right. So, this I may not be needed actually, but start with initial condition, then this I is needed, otherwise okay, fine. So, J is something like that, and this is like this actually. So, your Hamiltonian definition is nothing, Hk is nothing but Lk plus lambda k plus 1 transpose times Fk. So, Lk is nothing but this coming from here, and lambda k plus 1 times coming Fk is nothing but that. This is what your Hk Hamiltonian k. Now, what is the necessary conditions? Necessary conditions will tell that state equation, co-state equation, optimal control and boundary conditions of the thing, we know that. So, the state equation is like this, which is already given to us. Okay. The co-state equation is lambda k equal to del Hk by del xk. So, this expression now Hk is available from here. So, del Hk by del xk is nothing but qk xk from here, and ak transpose times lambda k plus 1 from here. Okay. So, that is what it is. There is no minus sign, remember that again. Lambda k is nothing but qk xk plus ak transpose times lambda k plus 1 sort of thing. Then optimal control equation, okay, del Hk by del uk equal to 0. So, if you apply that, Hk is again here. So, del Hk by del uk is one term is Rk uk, other term will be Bk transpose lambda k plus 1. Okay. So, this happens to be something like this actually. So, the boundary condition happens to be lambda n equal to Sn xn actually. Okay. Anyway, so this expression del Hk by del uk, what I was talking is something Rk uk plus Bk transpose times lambda k plus 1, that is equal to 0. Okay. So, obviously, what, okay, let me write it otherwise. Okay, Rk uk plus Bk transpose times lambda k plus 1 is equal to 0. So, if you solve this for uk, this is what you get actually. Okay. Very close to what we know before in continuous time. The only difference is not lambda t, but it is lambda k plus 1, which is anyway lambda t is equivalent to lambda k plus 1. So, that is what it is actually. The boundary condition happens to be something like this actually. Now, you have to use all these to derive some sort of a Riccati equation equivalent in discrete time actually. So, again we assume that lambda k has to be like pk times xk. Then what happens, you can go ahead and tell, okay, xk plus 1, what you get state equation here, nothing but ak xk, okay, plus bk uk, but bk times uk is nothing but this is what it is, and lambda k plus 1 is nothing but pk plus 1 xk plus 1. So, all this is substituted here. You start with xk plus buk, uk is like that, minus r inverse b transpose lambda k plus 1. And then lambda k plus 1 from this expression is nothing but pk plus 1 times xk plus 1. So, that is also substituted here. Now, what you can do is you see some xk plus 1 here, xk plus 1 here. So, you take it to one side and then write xk plus 1 is something times xk plus 1 is this equal to ak xk, and hence xk plus 1 can be given as some sort of some expression like that, which is nothing but a forward recursion actually. Okay. Then what about co-state equation? Co-state equation turns out to be like this, qk lambda k is nothing but qk xk plus ak transpose times lambda k plus 1, lambda k plus 1 again pk plus 1 times xk plus 1, and then this lambda k is pk xk. So, substitute all that. Now, xk plus 1 we just substituted, we just derived this expression. So, this instead of wherever xk plus 1 is there, I can write it that way. And then everything happens, pk xk is nothing but something big matrix actually multiplied with xk. And since xk is not 0 in general, and this equation holds good for all state sequence for any xi, that means it is valid for x1, x2, x3 everywhere actually. For all of those x will not be 0, because you are not talking about a equilibrium condition sort of thing. Okay, I mean, because this because this is not 0, if I take everything into one side and write it equal to 0 where xk is non 0, then obviously using our standard philosophy, the coefficient has to be 0, and that essentially equivalently stating that it is nothing but pk, what we get here is equivalent to that actually, okay, whatever you get here. Okay. So, essentially if you see this equation is nothing but a Riccati equation, it is a backward recursion sort of thing. If you know pk plus 1, you can calculate pk. Okay. So, this is what it is actually. So, essentially what we got is some sort of a discrete time Riccati equation, some sort of a backward recursion, which makes a lot of sense compatible to what we know earlier already basically. This is what it is actually. Now, you can stop here, but you can also use this matrix inverse lemma sort of thing, which is available and many people use it for a variety of reasons. And then if you use this lemma, then this expression what you have here can be expressed as something like this. Just substitute, just identify what is a, b, d, c in this expression, okay, and then a is nothing but identity, for example. So, like that actually put it there and then substitute expand and you will get it something like this actually. This is popularly known as this Riccati equation in discrete time sort of thing. Okay. Now, what about boundary condition actually? So, Pn is nothing but lambda n is nothing but Pn xn, which is equal to Sf times xn from boundary condition. So, Pn is Sf actually. Okay. So, what you are getting here is same Riccati equation sort of ideas with same boundary condition basically. So, you start with the boundary condition and do this backward recursion sort of thing. Okay. Now, what about finally the control? Control is nothing but this minus R inverse V transpose lambda k plus 1 sort of thing. So, uk is this expression and lambda k plus 1 what we got here. Okay. Wait a second. Okay, here lambda k plus 1 is nothing but pk plus 1 times xk plus 1 sort of thing. So, that lambda k plus 1 nothing but pk plus 1 times xk plus 1 actually. Okay. Alright. So, anyway, so this is what I mean here is uk is equal to like this and then you substitute lambda k plus 1 is pk plus 1 plus into xk plus 1. Xk plus 1 you can substitute using this the state equation and all, and then you can see that you have this uk appearing both sides. You take everything to one side and then keep the xk in the right hand side, and ultimately you can write uk as nothing but this inverse, whatever you see, this inverse times this matrix, okay, times xk. So, whatever you get all the things here, if you do that, there is nothing but the gain matrix, essentially a Kalman gain sort of thing. Okay. So, essentially we can again write uk is nothing but minus kk times xk, where kk comes from this expression actually. Okay. So, very close to what we know earlier, okay, but not exactly one to one sort of thing actually. Now, it interestingly turns out that in discrete formulation, this continuous this discrete time Riccati equation need not be very well behaved as a continuous time Riccati equation really. Okay. In other words, the sequence can have several type of behaviors and the possibilities include something like this. If you start with Pn, it can actually converge towards 0, it can go up, go to infinity sort of thing, or it can converge to some p infinity which is actually non-zero. Okay. And it can have no convergence at all also basically. Okay. You understand, there can be 4 possibilities. It can converge to some 0 value, it can converge to a non-zero value, it can converge to a strictly positive value, okay, or there can be no convergence also basically sort of thing. But anyway, that is that's not the point. Point here is every time you apply this, you may not get a nice solution sort of thing basically. Okay, but if pk converges, okay, then for large negative k, evidently if pk converges, right, converges means what? It converges to some value basically. If it converges, then obviously it will get a constant value actually. Okay. So, in that case the algebraic Ricard equation there is this spelling mistake actually again, okay, here. Okay. This is Ricard equation, okay. The algebraic Ricard equation becomes this expression actually, okay. And also this algebraic Ricard equation can have non-positive, semi-definite, non-symmetric and even complex solution. So, this kind of things are not very good to see, but its effect actually you have to live with that actually. And in the limiting solution, if the limiting solution to ARE, that is this constant P matrix exists, then ultimately we can write the gain as something like this, which is nothing but a constant gain, and in that case UK is nothing but minus kxk. Okay. So, in other words, just because you have a formula and does not mean that it is a very good nice well behaved formula basically. Okay. So, all these conditions are met, then you can write it that way actually. Anyway, so this is the heart of this LQR thing basically. I mean LQR using discrete time actually. Now, anyway, as I told in the beginning that there are some primitive ideas of LQR design through least square formulation sort of thing, and let us have a glimpse of that before moving further actually. So, this idea is very appealing and very simple actually rather. So, you have a system dynamics. The whole difficulty started because we had to deal with states in addition to control actually. Okay. But how about representing all state vectors in terms of control vector? Then everything we can substitute in the cost function also as function of states at different grid points, and then talk about some sort of a static optimization which will minimize this cost function, because it will all be now function of control only basically. How do we do that? This is something like this, xk plus 1 is nothing but this one, we know that. So, let us say we start with x1 which is nothing but initial condition. So, x1 is equal to all zeros and all u's at these are all controls at various grid points actually. Okay. So, everything 0 plus identity times x1. So, that means the first row is nothing but x1 equal to x1 sort of thing. Okay. Now, x2 when I put a k equal to 1, this is x2 equal to a times x1 plus b times a times x1 plus b times u1 basically. Okay. Forget this k and all that, let us see, this is a time invariant sort of thing, or either way, or I consider the entries of this actually as time varying thing also basically, either way. So, let us be compatible, you just take some sort of time invariant A and B basically. Okay. If you do that, then it is x1 is nothing but x1 and then x2 is nothing but b times u1 plus a times x1. So, b times u1 nothing else, okay, plus a times x1 here. Okay. And similarly, if you continue, finally, you will get xn is nothing but this expression actually. You will start with something like a n minus 1 times b, again recursively again and again applying that, ultimately you will come up with this actually. Now, the question here is what happens here is all these variables can be substituted as all the variables in un, u1 to un, un minus 1 really, and x1. So, wherever this values appear, that x1, x2, x3, x4 up to xn, I can always substitute through this equivalent expression of the right hand side, and then what we interpret is this optimization problem as a optimization problem of these variables only basically. So, now we can excite the idea of static optimization and talk about solution of a static optimization problem actually. This is what is listed here. So, what you do is substitute the state variable in terms of the control variable and initial condition, and initial condition happens to be a fixed number, fixed vector sort of thing. So, that does not play a role in optimization, nothing that you can vary for x1 actually. Okay. Well, anyways, then you can do you can substitute that this expression back into your optimization formulation and interpret everything, okay, this cost function, and interpret that cost function now as a function of only u's actually. This constraint has already been taken care while formulating this, by the way. Okay. But the problem here is actually it results to a large dimensional parameter optimization. And what is parameter here is control vector actually. The control values at grid point 1, 2, 3, 4, these are nothing but the parameters. So, if you really want an accurate good solution, it requires a very huge dimensional static optimization problem. Depends on the number of grids into the number of control, into the dimension of the control vector really. If you have 3 controls and something like 1000 grid points, then it will have a 3000 variables for optimization sort of thing actually. And typically the number of grid points are not 1000, but is a lot more than 1000. So, you will have that many variables, and it is not very good to see that or handle that kind of a optimization problem actually. So, that is what is the problem. It results in a large dimensional optimization problem, which is actually not very good to see. So, that is why it is not very popular also basically. But this is essentially the idea of this transcription method, what you can see. I mean, if you can correlate very quickly, then it is nothing but the whole idea of having the grid points and then constructing a large dimensional optimization problem, static optimization problem, is nothing but direct transcription ideas actually. Anyway, so the problem is like this, hence it is not that popular actually. Now, the final thing before we stop this lecture is what I promised is how do you use this discrete LQR setting for command tracking problems as well actually. Okay. So, here the problem setting is like this, you have this state equation and you have output equation also, and objective is that output your yk should track some reference output zk. Zk is available and yk should be able to track zk actually. Okay. So, what is our performance index? Performance index can be, remember what is yn is nothing but cn xn, and that should be as close to zn as possible. So, that is how we formulate a cost function outside the summation sign is like this, cn xn minus zn transpose sn times this actually. On the way, this deviation has to be minimum also basically. So, if you take cxk, yk minus zk, that has to be minimum, and what is yk? Ckxk. So, yk minus zk is nothing but ck xk minus zk. So, that has to be minimum actually, and also we want control minimum. So, this is how it is possible. Now, we follow with this Hamiltonian concepts and all. So, we have this h of k, which you can write Lk plus lambda k plus 1 transpose times f. So, this is nothing but your Lk plus lambda k plus 1 times k plus 1 transpose times xk plus 1, that is nothing but xk plus bk uk basically, our transpose f basically. Okay. Now, what you do is state equation, co-state equation, optimal control, boundary condition, all that we apply. Okay. And remember the difference here, the basic fundamental difference here is the cost function actually. You have, instead of a standard x transpose qx, you have something like this, and outside instead of arbitrary quadratic expression, we have that actually. That is the only difference. Okay. So, we apply all that. Now, you see lambda k is nothing but this expression basically, where it is lambda k is a function of xk, it is a function of zk as well, and it is also a function of lambda k plus 1 actually. Okay. This is a straightforward algebra from the basic principle sort of thing. Then optimal control del sk by del uk has to be 0. So, that explains that we again end up with the same expression there actually. Boundary condition, of course, del phi by del xn, which is actually equal to all this expression, because phi expression is something like this actually. Alright. So, now what happens here, the fundamental difference is lambda k equal to p k x k will not do the job. You will need also some sort of a time varying additional term, which will hopefully do the job actually. That will try to track that command, that will help tracking the command zk, which is coming externally. Remember, the problem is not to track the 0 signal, it is to track some sort of a non-zero signal actually. Okay. Now, the state equation turns out to be something very similarly what you have done before, we will proceed the same step. The only wherever lambda k or lambda k plus 1 is there, you have to be slightly careful to use this expression with this bias term, this minus gk sort of thing. Okay. That is what is done here. You can start with state equation, you will end up with lambda k plus 1, substitute it lambda k plus 1 in this expression, what you get here. Okay. And then again you have xk plus 1 here, xk plus 1 here, and then try to sort it out, take it to one side and then solve it, and then tell okay, xk plus 1 has to be the inverse of this matrix times whatever is left out, that is ak xk plus this term actually, okay, which is coming from this term. So, essentially we will end up with xk plus 1 is something like this, which is again a forward recursion formula actually. Okay, ak xk plus ek is defined something like this basically. So, what you have here is I plus ek pk plus 1 in whole inverse times xk plus ek gk plus 1 actually. This is again exactly the similar sort of idea, similar steps and all that, but we have taken a you have to be slightly careful to substitute lambda k's and lambda k plus 1s properly basically. So, with that the co-state equation turns out to be something like this, okay, and we are defining some terms and all that there. So, lambda k is a function of x k and z k and lambda k plus 1, right. So, that is what you see here, this is what v k x k minus w k z k plus I k transpose times lambda k plus 1. So, that is substituted here, okay, let us put it here, and lambda k plus 1 now we substitute whatever that is, and then you know that actually this x k plus 1 you have actually just solved it. So, this x k plus 1 you can substitute here, okay, and then lambda k is nothing but p k x k minus z k, that is your co-state equation, right, this one. Where are we actually? Okay, x k plus 1 is something like this, lambda k is something like this, and p k and x k plus 1 I have substituted, okay, I get it something like that. Okay. Now, if you substitute the co-state equation, then this lambda k is nothing but that, because that is the definition, right. We started like this. So, you substitute like that in left hand side, right hand side like that actually. So, rearranging the terms, it turns out to be like something into x k plus all these terms, it should be equal to 0. And again I strongly suggest all of you to kind of derive all these for your clarity and things like that. You can pause this whenever you see this lecture, you can pause it here and then try to derive it, these expressions yourself actually probably. Anyway, so we do that, and then this is what it is, you get some expression like this, and since it should hold good for all x which is non-zero and things like that, all sort of variations possible. Then what you can see is the coefficient has to be 0, that will give us the expression for p k happens to be something like this, and g k happens to be something like this. Remember g k can be known only with the available information about g k plus 1. Okay. So, this is a backward recursive formula again actually. Okay. So, boundary condition you can go there, and lambda n turns out to be p n x n minus g n. Okay. So, and then lambda x n you can substitute all the variables whatever you know there, and then this leads to this, okay, if you consider this, I mean equate these coefficients and things like that, then p n happens to be like this and g n happens to be this expression actually, that is what is written here. Okay. So, what you are getting is some sort of a backward recursive relationship for p k and g k, because p k is a function of p k plus 1 and g k is a function of g k plus 1 actually. So, these two backward recursion relationship also demands these boundary conditions actually. So, starting from these boundary condition you can keep on computing this p k's and g k's basically. Now, the control solution finally, that is what our main aim, u k equal to minus r inverse r k inverse b k transpose times lambda k plus 1, and this actually that lambda k plus 1 you can substitute it like this, and then okay, x k plus 1 you can substitute again. Okay, x k plus 1 is nothing but the state equation. So, that is a x k plus b u k sort of thing, you can substitute here, and then you expand the terms, okay, x k term and then u k term and g k plus 1 terms like that. Now, you have a u k in the left hand side and u k in the right hand side. So, you combine them together and then solve for u k actually, and u k will turn out to be something like this, which is, and this part of the solution can be defined as some sort of a gain matrix, and this gain matrix turns out to be all these expression, and then there is a bias gain matrix sort of thing basically. This is a reference signal, remember g. Okay. This is bias, right? G starts from something like this actually. The g k is somewhere here. So, this bias term, okay, coefficient is given this way. So, essentially you will end up with a formula which will tell you that u k is not only minus k into x k, minus k k into x k, but we have an additional term which tells you L k times G k plus 1 actually, which makes sense because you want to track some sort of a signal, reference signal actually. That is it. As I mean in this particular lecture I wanted to give some sort of an overview of discrete optimal control followed by discrete LQR, and there are many things around that. But now with the advancement of these digital computers and all that, you can actually implement any continuous time control formulas with a very small grid size also, and then the discrete optimal control will have very close meaning as what is continuous optimal control as well actually. So, with that knowledge we will stop this lecture, and also remember that this discrete LQR formulation and discrete optimal control formulation, all that we will use it at some point of time later in a slightly different settings actually, to come up with numerical algorithms for nonlinear optimal control also basically. So, with that motivation I will stop here. Thank you for your attention.